Hi students, as a part of IR spectroscopy, today I am going to discuss with you about the very important concept of IR spectroscopy, that is the conditions for IR activity or OR, criteria for IR activity. That is, we are going to discuss about what are the molecules which are IR active and what are the molecules which are IR inactive. So what do you mean by IR active molecules? The molecules which gives IR spectra are called as IR active molecules. On the other hand, if the molecules do not give the IR spectra, then those molecules are called as IR inactive molecules. So let us start with the first condition or criteria of IR activity. So first condition is, if in a molecule there is a change in dipole moment by vibrations. If in a molecule there is a change in dipole moment by vibrations, that is with the help of vibrations. So stretching is one kind of vibration. So with the help of stretching or with the help of any vibration, if there is a change in dipole moment in the molecule, then we can say that that particular molecule is IR active molecule, and since it is IR active molecule, then we can record the spectra of that particular molecule. Now what do you mean by dipole moment? So dipole moment is usually, that is, mathematical expression for the dipole moment is mu equals to QD. Mu equals to QD. Where mu is the dipole moment, Q is the charge, and D is the internuclear distance between the two nuclei. We are well versed with this. So for example, if we take HCl or HBr, let us take HBr. Now let us say that this is the nuclei of the hydrogen and this is the nuclei of bromine. Hydrogen. Now this is the internuclear distance between the hydrogen and bromine of the hydrogen bromide molecule. So this is the internuclear distance. Now the bond between the hydrogen and bromine is elastic. The bond is basically elastic. So since it is elastic, if it is stretched by the vibrations, if it is stretched, what happens to the internuclear distance? If it is stretched, then what happens is the bond will stretch in this manner. Now the internuclear distance between the hydrogen and the bromine is increased. Now when the internuclear distance is increased, so definitely there will be a difference in the dipole moment, because the internuclear distance D and mu both are directly related. Now initially the internuclear distance was this. Now whenever we stretched the bond between the hydrogen and bromine, then the internuclear distance has been changed. As the internuclear distance between the hydrogen and the bromine has been changed, and as the internuclear distance and the mu, that is the dipole moment, both are directly related, definitely there is a change in dipole moment. So if there is a change in dipole moment by vibration, so what are the vibrations? Yes, stretching is a vibration, right? So if there is any change in the dipole moment by vibrations, then those molecules are IR active molecules. Those molecules can be recorded in the IR spectrum. That is, they will give the IR spectrum. So examples are hydrogen chloride, hydrogen bromide, etc. So this is the first condition or criteria for IR activities. So coming to the second condition or criteria for IR activity is, if the molecule contains permanent dipole moment. If the molecule contains permanent dipole moment, that is, if mu is nothing but the dipole moment. If mu is not equal to 0, then the molecule is 100% IR active. No doubt in it. If the molecule contains permanent dipole moment, then all the vibration modes of the molecule are IR active. All the vibration modes. All the vibration modes means what? So do remember, students, whenever the IR radiation is irradiated on the molecule, then molecule undergoes many vibrations, that is, so many vibrations, by which we will get many vibrational modes. Many vibrational modes we are going to get. What are those vibrational modes we are going to discuss in the subsequent classes. So whenever the IR radiation is irradiated on the molecule, then already we know that vibrational transitions takes place, by which so many vibration modes we are going to get. Now, if the permanent dipole moment of the molecule is not equal to 0, that is, what do you mean by that? If the molecule's dipole moment is permanent, then all its vibration modes are IR active. All its vibration modes are IR active. So since all its vibration modes are IR active, so definitely this molecule can be recorded in the IR spectra. That is, IR spectra of such molecules can be recorded. That is, mu should not be equal to 0. If mu equal to 0 and vice versa, if the molecule is not associated with the permanent dipole moment, then what happens? Then the mu equal to 0. If mu equal to 0, it will not give any sort of IR spectrum. Those molecules are called as IR inactive molecules. Now let us see what are those molecules whose permanent dipole moment is 0. Now generally, which molecules will have the permanent dipole moment, students? The polar molecules. The molecule containing the polar bonds. Right. The polar molecules have the permanent dipole moment. Now, what are the examples of the polar molecules which will have the permanent dipole moment? The polar molecules which will have the permanent dipole moment are HCl is one of the examples. HBr is another example. Next, ammonia is another example. Phenol is another example. Alcohol is another example. So many we can give, so many examples. Alcohol, etc. So this is the second criteria or condition for IR activity, students. That is, if the molecule has permanent dipole moment. Now, by seeing the structure of the molecule, we can say that that particular molecule is having the permanent dipole moment. How? If it is a polar molecule, definitely it will have the permanent dipole moment. If the molecule have the permanent dipole moment, all the vibration modes of the molecule are IR active. So since all the vibration modes of the molecule are IR active, so definitely those molecules, those polar molecules are IR active. Since they are IR active, they are easily recorded in the IR spectra, giving the IR spectra. So this is about the second condition. So coming to third condition. So third condition is, if the dipole moment of the molecule is zero, mu. If the dipole moment of the molecule is zero, only those vibrational modes of the molecules are IR active, which brings the change in dipole moment. If the dipole moment of the molecule is zero, only those vibrational modes are IR active, which brings the change in dipole moment. So in the previous case, when the molecule is associated with the permanent dipole moment, in that case, all the vibrational modes are IR active. But whenever the dipole moment of the molecule is zero, only those vibrational modes are IR active, which are recorded in the IR spectrum, which brings the change in dipole moment. Now in this case, all the vibrational modes are not IR active. Even though all the vibrational modes are not IR active, due to some vibrational modes, it becomes IR active and it can be recorded in the IR spectra. IR spectra of such molecules can be recorded. For example, carbon dioxide. So what is the structure of carbon dioxide, students? C double bond O, double bond O. C double bond O, double bond O. So we are well versed that the carbon dioxide dipole moment is zero. Carbon dioxide dipole moment is zero. So since the carbon dioxide dipole moment is zero, it should be IR active. But already have discussed that. Whenever we are irradiating the IR radiation onto the molecules, then it undergoes vibrational transitions, resulting in the formation of n number of vibration modes. So in the similar fashion, whenever the IR radiation is irradiated on the carbon dioxide molecule, then vibrational transitions takes place, resulting in the formation of n number of vibration modes. Right. Among n number of vibrations, what are those vibration modes? We are going to discuss in the subsequent classes. So let us say that this is one of the vibration mode in which the right-sided oxygen has been stretched and the left-sided oxygen has been stretched. Right. Now here it is similar to the carbon dioxide structure. The right-sided oxygen atom has been stretched and the left-sided oxygen atom has been stretched. There is no change in the dipole moment. If there is no change in the dipole moment, mu equal to 0. If there is no change in the dipole moment, such vibration mode is not IR active. This is not IR active. This is not IR active. Because what is happening? We are stretching. It is subjected to stretching. But what is happening? The internuclear distance between the carbon and oxygen on the right side and the internuclear distance between carbon and oxygen on the left side, both are one and same. So if the internuclear distance is one and same, definitely dipole moment will be 0. So when the dipole moment is 0, So definitely such a vibrational mode is not IR active. But if we see these two vibrational modes, that is, let us say that the left sided oxygen has been not stretched, whereas the right sided oxygen has been stretched. This is one of the vibration. Now, internuclear distance is not same, because in this the internuclear distance between the carbon and oxygen, right sided oxygen is more, and the internuclear distance between the carbon and left sided oxygen is lesser. Yes. So due to difference in internuclear distance, so definitely there will be a dipole moment. So when there is a dipole moment, it becomes IR active. So in the similar fashion, let us say that the carbon, the right sided oxygen has not been stretched, whereas the left sided oxygen has been stretched. Now the internuclear distance between carbon and the right sided oxygen is lesser, whereas the internuclear distance between the carbon and the left sided oxygen is more. So internuclear distance has been changed. So when the internuclear distance is changed, as the internuclear distance is directly related to the mu, that is the dipole moment changes. When the dipole moment changes, obviously it becomes IR active, so it gives IR spectrum. This is also IR. So this is one of the vibration mode of the carbon dioxide, which is IR inactive. These are the two of the vibrational modes of the carbon dioxide which are IR active. So do remember, students, in order to record IR spectrum of the molecule or IR spectra of the molecule, if at least one vibrational mode is in such a manner that dipole moment is not equal to 0, if there is a dipole moment associated with that vibrational mode, so definitely that particular molecule can be recorded in the IR spectra. That particular molecule will give the IR spectrum. Right. I hope you understood this. So coming to fourth condition. All diheteroatomic molecules are IR active. All diatomic molecules are IR active because they have a permanent dipole moment. All diatomic hetero molecules, diheteroatomic molecules, because they possess permanent dipole moment, like HCl. Okay, so before that, so we have to discuss some example of this category, right? That is this category. So let us discuss the example of this category. So example of this category are, so one is carbon dioxide, done. Next is methane, PCl5, SF6, IF7, benzene, naphthalene, anthracene, etc. So here in these molecules, not all the vibration modes are active. IR active. Only one or two vibration modes of these molecules are IR active, which is sufficient for the molecule to get recorded in the IR spectrum. They will give the IR spectrum. No doubt in this. Now these molecules dipole moment is not equal to 0. Their dipole moment is 0. The dipole moment is 0, but due to some of the vibrational modes, they will get some dipole moment by which they will become IR active. Right. Now do remember, students, that how to find out whether it is a polar molecule or non-polar molecule. So in such a molecule definitely mu equal to 0. No doubt, dipole moment is 0. So benzene, naphthalene, already you know the anthracene, because all are forwards, non-polar. Directly we can say that. Methane, we can say that. PCl5, SF6, IF7. Directly by seeing them, we cannot say that it is non-polar molecule. If it is polar like HCl, HBr, ammonia, phenol, ROH, alcohol, ROR, all that, water comes under this category. Then they are polar molecules. Since they are polar molecules, definitely they are associated with dipole moment. So since they are associated with dipole moment, they are IR active, no doubt in that. But here, how to find out whether these are polar or non-polar? So do remember, students, that if the central atom is surrounded by similar atoms and the central atom do not contain the lone pair of electrons, then definitely that molecule's dipole moment is equal to 0. So see, what is the central atom, students? Here carbon is the central atom. It is surrounded by same atoms, all hydrogens. So there is no lone pair. So such a molecule is non-polar. So non-polar means mu equal to 0. So similarly, phosphorus. Phosphorus is a central atom, right? And it is surrounded by same chlorine atoms. And the phosphorus central atom do not contain the lone pair of electrons. So it is non-polar. Similarly, in this SF6, sulfur is a central atom. It is surrounded by similar atoms. And the sulfur central atom will not contain any lone pair of electrons. So mu equal to 0. Next, similarly, iodine is a central atom, and it is surrounded by similar 7 fluorine atoms. And iodine will not contain any lone pair of electrons. Mu equal to 0. We know about the benzene, naphthalene, and anthracene as well. So here the mu equal to 0, but due to some of their vibrational modes, they become IR active. Keep this in the mind. Just like carbon dioxide. So now coming to the fourth one, students. All diheteroatomic molecules are IR active because their permanent dipole moment is not equal to 0. They will possess permanent dipole moment. All diheteroatomic molecules like HCl, polar molecules only, HBr, HF, next CO, NO, etc. Because they are polar. So already I have discussed the polar molecules will have the permanent dipole moment. So this is the fourth criteria. Fourth condition. So last criteria or last condition is all homodiatomic molecules. all homodiatomic molecules are IR inactive. Homodiatomic because they are non-polar. So as they are non-polar, they will not associated with any dipole moment. All homodiatomic molecules. Examples: hydrogen molecule, nitrogen molecule, next oxygen molecule, fluorine molecule, chlorine molecule, bromine molecule, iodine molecule, etc. Why? Because they are non-polar. If they are non-polar, definitely mu is equal to 0. If mu equal to 0, so definitely they becomes IR inactive. So by seeing this particular molecules polarity and non-polarity, so we can easily guess whether that particular molecule will give the IR spectra or not. I hope you understood this. So once again, to recapitulate, the first condition or criteria for IR activity is if any molecule changes its dipole moment by vibrations, then it is IR active, which can be recorded in IR spectrum. Whose IR spectrum can be recorded? Second. What is the second, students? The molecules containing permanent dipole moment. The molecules containing permanent dipole moment are IR active, which will give the IR spectrum. Examples: all the polar molecules. And in the second case, all the vibrational modes of the molecules are IR active. So coming to third condition, if the dipole moment is 0, only those vibrational modes are IR active, which brings the change in dipole moment. Like carbon dioxide example. So in the carbon dioxide are associated with so many vibrational modes. So out of so many vibrational modes, these two vibrational modes are IR active. Why? Already I have explained. And by seeing the molecule, we can decide whether it is polar or non-polar. Right? Polar, already you know that. So in order to decide whether it is non-polar, just you have to see the central atom. If central atom is surrounded by similar atoms and it do not contain, that is central atom do not contain the lone pair of electron, so definitely the dipole moment of such molecules is equal to 0. Since equal to 0, they are IR inactive, but due to some of their vibration modes, they will become IR active. So their IR spectra can be recorded in the IR spectrum or IR spectrum. So, and the next one is the fourth condition or criteria is all heterodiatomic molecules. All heterodiatomic molecules are IR active because they are polar, like HCl, HBr, HF, CO, etc. The last one is all homodiatomic molecules are IR inactive. Why inactive? Because they are non-polar. So since they are non-polar, their dipole moment is equal to 0, like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, etc. I hope you understood this. So with this information, we are going to dive into the IR spectroscopy in the next video. Thanks for watching.